You awake in the middle of the night to find that your slovenly roommate has once again left the dorm room door open. Being too tired to get up and close the door, you grab a nearby slice of pizza and fling it at the door. It strikes the door as shown in the figure below and sticks to the door. Treat the pizza as a point object that strikes the 1.5 kilogram door 0.8 meters away from the hinge. A. Determine the angular velocity of the pizza-stained door just after the collision, and B. Determine the time for the pizza-stained door to rotate by 1/4 turn. Assume no friction so that the door moves with constant omega. In this problem, what we notice is a collision between a flying piece of pizza and a door. When we examine a collision, we ask whether there are external forces, and if no, momentum will be conserved. We ask also whether there are external torques, and if no, then angular momentum will be conserved. In this problem, there are external forces, and they come from a subtle place. If the door were not attached to the hinge, rather than simply swinging shut, the door would go tumbling into the hallway itself. However, the hinge applies a force that keeps that edge of the door aligned with the door frame. Since the force applied by the hinge is applied at 0 radius, i.e. 0 distance to the pivot, even though that force is there, there is no external torque. For this reason, momentum is not conserved in this problem, but angular momentum is. To solve the angular momentum problem, we'll select two moments, and whenever we have a collision, these two moments will always be just before and just after the collision itself. And our plan is to connect moment 1 to moment 2 using the principle of conservation of angular momentum. As always, conservation of angular momentum will be realized by totaling the angular momentum at moment 1 and setting that total equal to the angular momentum at moment 2. Clearly, at moment 2, with the door swinging closed, there is an angular momentum because it is rotating around the pivot created at the hinge. Less clear is that there is also an angular momentum at moment 1. The door is not moving, but the pizza is. Any linear momentum might be an angular momentum if the linear momentum is directed off-axis or away from the pivot point in some problem. Examining the diagram more closely, we find that the momentum of the pizza is directed along the vector shown and is directed toward the point R, which is 0.8 meters away from the hinge itself. Point objects will have an angular momentum equal to the cross product between the radius vector and the linear momentum that the object carries. Looking closely, we notice that this angular momentum will be directed counterclockwise around the hinge and will be of an amount r crossed with p. Since r and p are perpendicular to one another, we won't need a sign of any angle, but we'll simply be able to write the radius lowercase r times the momentum, which is expressed as m times v. In the initial moment, the door has no angular momentum, and so this finishes our total for the angular momentum before the collision. After the collision, we will have a pizza-stained door, and the total moment of inertia of that pizza-stained door will include the moment of inertia due to the slice of pizza, as well as the moment of inertia of the door itself. This door will be moving with some angular velocity, omega subscript 2, and to complete the calculation, we'll have to find results for both the moment of inertia of the pizza as well as the moment of inertia of the door. Let's begin with the door. The door is shaped as a rod rotating around its end, and the moment of inertia of a rod rotating around its end is 1/3 the mass of that rod times its length squared. We're asked to treat the pizza as a point object. The moment of inertia of any point object is its mass times its radius squared. Now this is not the radius of the slice of pizza, this is the radius of the circle around which the point object rotates. And we see from the diagram that that radius is 0.8 meters, and we need to square it to get the result. Plugging in all these terms, we have the following equation, with radius times mass times velocity on the left, and moment of inertia times omega on the right. Here, the radius times mass times velocity term on the left-hand side of the equation is entirely in MKS units, meters, kilograms, and meter per second for the velocity. This means that the right-hand side must also be in MKS units. Our moment of inertia is clearly in kilogram meter squared, and this implies that the omega of this equation must be in rad per second, which are the proper MKS units for an angular velocity. We can then solve for the angular velocity omega 2 to get the result 0.694 rad per second, which is the answer to part A of our question. For part B, we are asked to determine the time for the pizza-stained door to rotate by a quarter turn. This is a kinematics problem. Since we are asked for a time interval, we begin by formulating the question when. This is an ill-formed question. We need to say when what. To specify a quarter turn, we recognize that turns are an angular distance and therefore represent an amount theta. Because our omega is in rads, we won't express the question as time when theta is 90 degrees, which is a quarter turn, but rather we'll ask for time when theta is pi over 2, so that the units on theta and the units on omega are consistent. We're told that the pizza-stained door moves with a constant omega. That means that the alpha of the pizza-stained door is 0, leading us to the simple form that theta is theta 0 plus omega 0t. Using the initial location as 0, we plug in what we need. The only unknown is time, which yields the result 2.26 seconds.